Hi everyone, and welcome to this week's lesson for Leaving Cert Higher Level Maths as part of our exam countdown. As you can see, this week we're going to be having a look at coordinate geometry, the circle. So the circle is always a huge part of paper 2 normally of the Leaving Cert. And we're going to have a look at a couple of things today. We're going to start off with some basics, but before I start, just to let you know that you'll see two links to two very useful videos in the chat. The first one there looks at circles that have x and y axes. It has the x and the y axis as a tangent. And the second one is looking at finding the equation of a circle when you're given three pieces of information about the circle. Okay. And what you'll see is we have page 18 and 19 of the exam of the log tables cut out here. And again, I suppose I've used 18 and 19 because a lot of the formulae that you're using for the line, they're going to come in quite useful in the circle also. So they're all on page 18 and the top of page 19. And then the bottom half of page 19 goes through our important formula for the circle. So that first one that I've highlighted there is the first formula for the circle that we're looking at, the equation of a circle. And as you can see there, it gives you all the information. The center is HK and the radius is R. And if you go ahead and you multiply out these brackets here in that equation of a circle or that formula, you will end up with an equation something like this down here. So that one down there, that's the one we call the general equation of the circle. So it's basically, these two are equivalent, if you like, but one is just the multiplied out form of the other. And you can see there as well, very important, minus g minus f is your center, and your radius is the square root of g squared plus f squared minus c, where g, f, and c, they're just numbers, okay? So they're going to become quite useful also. And another formula for the equation of a circle that you might have learned during your studies is x squared plus y squared equals r squared. So this again is just a different kind of form of this. And with this one, the center is at 0, 0. So it's not one that comes up that often, but it's a nice easy formula. Your center is at 0, 0 and your radius is r as normal. So let's just go back over here to where we have a little bit more space, and just going to go through very quickly just a couple of things to do with the circle before we have a look at a couple of the exam questions. So we've mentioned the three equations of the circle. The second thing then, just to remember, I suppose from junior cert, to remember that if we have a circle and we have a tangent to the circle, so remember a tangent is a line that will touch the circle at one point only. So it's looking like there is the point it's touching it. And if I'm to draw a radius, so the radius comes from the center of the circle out to that point, that radius is always going to be perpendicular to the tangent at the point of contact. So let's just write that out for ourselves. The radius is always perpendicular to the tangent at the point of contact. So what I mean by the point of contact is that's where the tangent contacts the circle. So it's right there in this case. It's the point where the tangent touches the circle. So that's a theorem from our junior cert studies. Radius is always going to be perpendicular to the tangent at the point of contact. And that becomes quite useful when we're looking at slopes of radii and slopes of tangents. The second thing about a tangent, tangents are quite important with in coordinate geometry, the circle. The second thing is if we work out the distance from the center to the tangent, so we'll talk about how we would do that in a second, but if that distance from the center to the tangent is equal to the radius, or sorry, I should say from the center to a line, I suppose, we're not quite sure if it's a tangent yet. If that's equal to the radius, well then therefore the line will be a tangent. Okay, so the distance from the center to a line, if that's equal to the radius, that will be a tangent. And that just makes sense here. If I was to work out this distance along that line there, and if that was the distance of, if that was equal to the radius, well, the line is a tangent. If it wasn't, well, then you're going to have something like this. You're either going to have this situation where you have a circle there's the center, and you've a line way out here. So if you calculate the radius, it's going to be slightly shorter than the distance from that center to the line. Or you might have this situation here where you have a circle center and you have a line cutting through the circle at 2 points only. So if I work out my distance from the center to the line in this case, it's going to be ever so slightly shorter than the radius. So in this case over here, I suppose the line and the circle don't really have any relationship. In this case here, the line is going to be a chord to the circle. Why a chord? Well, it touches the circle at 2 points on the circle. So your diameter, if you like, that's actually a chord of the circle. It's a very specific or a very special chord, but it's still a chord because it's touching the circumference of the circle at 2 points only. Okay. The next thing we'll have a look at is if we're looking at points and circles. So we have three cases here. We have three circles and they each have their center there. And we have three cases, three things that could happen here. We could end up looking at a point that lies somewhere inside the circle. We could end up looking at a point that's somewhere on the circle, so on the circumference of the circle, or maybe the point is somewhere outside of the circle. So similar with what we did with the line, to check if the point lies on, so on in this case, inside in this case, and outside the circle here, what we would do is we would sub that point into the circle. So we'll have the equation of the circle and we'll sub the point into the circle. If it's this case on the left-hand side, so if it's this case here, then the left-hand side of the equation, once you've subbed it in, should be less than the right-hand side. If it's this case in the middle, the left-hand side should be equal to the right-hand side. So in other words, the line or the point should satisfy the equation of the circle. And therefore, we can say that the point is on the circle. And you've probably guessed it, but if it's this case over here where the point lies outside the circle, you have the left-hand side will end up to be greater than the right-hand side. So when I say the left-hand side and the right-hand side, you remember you're subbing the point into the circle and you're working out what that left-hand side gives you and what the right-hand side gives you. So subbing it into the equation of the circle. And the last piece of information is we might look at two circles, and we're going to look at this in a second, but two circles that either touch externally, like these two, or you could have two circles where one sits right inside the other. Excuse my drawing, I'll try my best. So you have this case where the circles touch externally, and you have this case over here where they touch what we call internally. So their touching point is inside the circle, whereas here they're touching externally. And a diagram is really, really useful here because in this case, if you add the radius of the first one, so we call that R1, to the radius of the second one, well, that should be equaling the distance between, so there's my distance between my centers, and we'll call that distance D. So if the distance between the centers is equal to the first radius plus the second radius, therefore the circles touch externally. And you've probably guessed it over here. There's my first radius, there's my second radius, and there's my distance between the centers. So if the distance between the centers is equal to the first radius, so there's R1 and R2, minus my second radius, well then the circles are going to touch internally. Okay, so that's just, I suppose, a little bit of background information on some things. Now, I haven't covered everything, but on some things that you'll have come across in the circle. So, like I said, this one up here, that's a theorem from junior cert. If the distance from the center to the line is the same as the radius, well, then you're going to have this situation up here where it is a tangent. If the distance from the center to the line is bigger than the radius, you're going to end up with this situation down here where they've no relationship. And if it's smaller, well, then it's going to be what we call a chord. We've looked at the relationships between points and circles, whether they're inside, on, or outside. And we've just looked at the circles touching externally and internally. And like I said, don't forget about your formulae in the log tables, page 18 and page 19. And this one, I suppose, that's going to become quite important here too. The distance from a point to a line, especially if you're checking if a line is a tangent to a circle or not. Okay, so that's just, like I said, a brief introduction to the circle, but we're going to come across a lot more things when we're doing the exam questions too. So we're going to make a start on an exam question from a good few years ago at this stage. So this is 2012 paper 2, and we're looking at question 2. So this is a nice little question, getting us used to those basic things from the circle. So the equations of two circles are given. There's my two circles, and I'm just going to make a note for myself. They're given in general equation form. So from page 19 of my log tables, I see that they're given in the multiplied out form, if you like. X squared plus y squared plus 2gx plus 2fy plus c equals 0. And it's up to us to try figure out what that g, what that f, and what that c is. So the first thing it asks us to do in part A, write down the centre and the radius length of each of the circles. So the centre should be nice and easy. We know from our log tables it's going to be minus g minus f. But let's remind ourselves, look where the plus 2g is. That's the coefficient of the x. So my plus 2g is going to be minus 6. So 2g is going to be minus 6. And look where my plus 2f is. That's the coefficient of the y. So that's going to be minus 10. So to find g, I would divide across by 2. So that will give me minus 3. And to find minus g, which is what I want for my centre, it's going to be plus 3. And similarly with f, it's going to be minus 5. And with minus f, it's going to be plus 5. So there's my centre straight away. It's minus g minus f, so that's 3 and 5. Minus g is 3, minus f is 5. Just a quick shortcut, I suppose, on doing that. Some people like to just go back up to your equation of your circle up here. And to find your centre, what we do is we take the coefficient of the x, so that's the number in front of the x. We have it and we change the sign, so that will give us 3. Do the same with the y. So minus 10, we half it, and we change the sign, we get 5. So you can jump straight to that if you've got a bit of practice with these ones. With your radius length, unfortunately, there's no such shortcut. We need to use our formula. So I've taken up a good bit of space here, but there's my formula from my log tables, and I'm just going to sub in. My g from here is minus 3, and I'm making sure that goes into brackets. My f from here is minus 5. And my minus c, be careful, your plus c is plus 29, so minus c is going to be minus 29. And that can go straight into your calculator. It should be giving you root 5. Okay, and we're asked to do exactly the same for the second circle. So that's what my box on the right-hand side is for. So what I'm going to do this the quick way. My minus g minus f, that's going to be half the x coordinate, or half the x coefficient and change the sign, so that's going to be 1. And half the y coefficient and change the sign, that's also going to be 1. So my centre for my circle 2, C2, is going to be 1, 1. Again, we need to use our formula for the radius. So subbing in, that's going to be, my g is going to be minus 1. So I know that because minus g is 1. So plus g must be minus 1. Just change the signs. My f is going to be minus 1. And be careful, my plus c is minus 43. So my minus c is going to be minus 43. And a minus by a minus gives us a plus. So that should be giving you, throw that all into your calculator, that should give you 3 root 5 for the radius. So obviously your second circle, C2, is the bigger one with the bigger radius. Okay, so prove that the two circles are touching. So we know that if they're touching externally, so this is what we've just said above, then the distance between the centres is going to be equal to radius 1 plus radius 2. And if they're touching internally, it's the opposite, then the distance between the centres is going to be equal to R1 minus R2. So regardless of which situation it is, well, we need to find the distance between the centre for both of them. So we're going back to page 18 of our log tables, and we're going to write down our formula for the distance between 2 points. Now, what 2 points are they? Well, it's the distance between the centres. So it's my two centres that I have up here. So I'm going to label my 2 points as x1, y1, x2 and y2, and all I'm doing is I'm subbing straight in to my formula here, so that will give me 1 minus 3 all squared in the first bracket and 1 minus 5 all squared in the second bracket. And we're putting that straight into the calculator. We should be getting 2 root 5 when you do that. And I would leave it in third form because look at what I've done with my radii. I've left those in third form also. So because my distance is 2 root 5, we know that this situation is probably out. And we know that by looking at our radii, if we subtract root 5 from 3 root 5, so let's do that, radius 1 minus radius 2, or vice versa, 3 root 5 minus root 5, that will give me 2 root 5, which is equal to the distance that we found over here. So make sure we conclude, make sure we answer our question. We're going to say, since the distance is equal to R1 minus R2, therefore the circles touch, and let's go a step further and tell them that they touch internally. Okay, and it's as simple as that. Part C, verify that 4, 7 is the point that they have in common. So let's have a look at a diagram for a second. It's very useful to draw a diagram. There's my first circle, and we now know that they touch internally. So they touch somewhere like that. And what they're telling us here in part C is that the point that they have in common, so this point here, we're being asked to check that that's 4, 7, or verify. So verify means check. So a couple of ways that you can do this, but probably the easiest way is to basically take that 4, 7 and sub it into the first circle and the second circle. And let's remind ourselves what we're looking for. We're looking for this situation here because we want to show that the point lies on the circle. So we're looking for that point to satisfy the circle, if you like. So we'll take 4, 7 and we will sub it into the first circle, which we're taking from the question, x squared plus y squared minus 6x minus 10y plus 29 is equal to 0. And what we're going to do is everywhere we see an x, we're going to replace it with a 4. Everywhere we see a y, we're going to replace it with a 7. So that should give me 4 squared plus 7 squared minus 6 times 4 minus 10 times 7 plus 29, and we're hoping that if that point lies on the circle, that it should equal to 0. So your job is to put all of this into your calculator, and that should end up giving you 0 is equal to 0. So therefore we can say that 4, 7 is on the circle C1. And we're just going to do exactly the same thing for the second circle. So we're going to sub it into x squared plus y squared, again taking this from the top of the page, circle 2. And everywhere I see an x, I'm going to replace it with the 4. Everywhere I see a y, I'm going to replace it with a 7. So we're getting 4 squared plus 7 squared minus 2 times 4 minus 2 times 7 minus 43, and we're hoping that that equals to 0. And again, just plug this straight into your calculator. We should be getting 0 equals 0, so therefore the point 4, 7 is also on the second circle, and therefore that's the point that they have in common as we were asked at the start, or in part C. Okay? And finally, part D, find the equation of the common tangent. So if we just go back to our diagram here, if the circles are touching at all, internally or externally, they're going to have a tangent in common. So there's my tangent, something like that. Now, I'm going to show you 2 ways of answering this question. First way is a little bit easier. Very, very easy way of finding a common tangent is, and the simplest way of finding a common tangent, we basically take our first circle and we subtract the second circle from it. And it is as simple as that. So if we take our first circle, which is x squared plus y squared minus 6x minus 10y plus 29, and from that we're subtracting our second circle. So because I'm subtracting, I'm just going to put it into brackets because we know that that minus is going to change the signs of everything that comes after it. And we put our equals to 0 at the end. So removing my brackets, I get x squared plus y squared minus 6x minus 10y plus 29. That minus is going to change the signs of everything that comes after it. So making that a plus 2x, a plus 2y, and a plus 43. And look at all the cancellation that we have. The x squared cancels with the x squared. The y squared cancels with the y squared, and we're ending up with minus 6x plus 2x. That gives me a minus 4x. We have a minus 10y plus a 2y. That's going to give me a minus 8y. And finally, with our constants, we have a plus 29 and a plus 43, and that's going to give us a plus 72. So plus 72, and we have our equals to 0 at the end. And that right there is basically your equation of your common tangent. Now, hopefully you see that. You can actually divide across here by 4. So 4 will divide into all 3 terms. And we can multiply or divide by minus 4, I suppose, or multiply across by minus 1 at the end. So in simpler terms, we should be getting 1x plus 2y minus 18 is equal to 0 for that one. Okay, and it's as simple as that. But like I said, there is another way of doing it, just to show you very, very briefly. What we could have done is we could have found the slope of that line there. So the slope of the radius from the center of either of the circles to the point 47, which is on the tangent, the common tangent. So we could find the slope. Let me just write this out for you here. So you could find the slope of the radius, and we're going to flip it and change to a perpendicular slope, because remember we said that the radius is always perpendicular to the tangent at the point of contact. And then you could use that perpendicular slope and the point 47 to find the equation of the tangent. So slope of the radius, flip it and change the sign to find the perpendicular slope, and then use that slope with your point 47 to find the equation of that line, that blue line that we have there, the tangent. Okay, but you'll get exactly the same answer. You'll get exactly as we've gotten here. I think that way is a little bit easier, to be honest, or a little bit quicker as such. Okay, moving up to 2019, paper 2, so a little bit more recent, question 3. And 2 parts to this question. The first part, the point minus 2k, they're telling us it's definitely on that circle. Find 2 possible values of k. So there's no question about it. The point definitely lies on the circle. So what we should be able to do is we should be able to sub in for x and y. And as we expect, as we said at the very start, the left and the right hand side should equal to each other. So I'm going to take my circle, and it's written in that form, x minus h squared plus y minus k squared equals r squared, but that's fine, we can work with that. Everywhere I see an x, I'm putting in minus 2, so that's coming from here. Everywhere I see a y, I'm putting in k, and everything else is staying the same. Okay, all we're doing is, because we know that it definitely lies on the circle, we know that the left has to equal to the right hand side. So in the first bracket, that's going to give me minus 4 all squared. In the second bracket, I square the first, I get k squared. I square the last, I get plus 9. And I multiply the first by the last and I double it, I get minus 6k. I'm also going to move that 65 across to the left to give me minus 65. So that's 16 plus k squared plus 9 minus 6k minus 65 equals 0. And just tidying up, we'll end up with a quadratic equation. K squared minus 6k, and putting your 3 constants together, that should give you minus 40 equals 0. So you've 2 choices here. It's a quadratic equation. You can go ahead and factorize it using guide number, or what I'm going to do is I'm going to use minus b formula. So my a is 1, my b is minus 6, and my c is minus 40. So subbing into my minus b formula, or writing out my minus b formula first. My variable is k, so that's why I have k equals. So subbing in, I'm getting k is equal to minus b, so that's going to be minus 6 plus over minus the square root of minus 6 squared minus 4 times 1 times minus 40 all over 2 times a, so that's 2 times 1. And you should end up with two possible values of k, and they asked for 2 in the question. So this time your answers should be k is equal to minus 4 is one of them, k is equal to 10 is the other. And we're fine to have a negative number here because it's telling us that k is an element of z, where z, remember, are your integers, positive and negative whole numbers. Perfect. Okay, so again, we couldn't answer that question unless we knew that the point was definitely on the circle. They had to give us that piece of information to make up for leaving out the k. Okay, second part of the question, and this is very, very similar to a question that's gone through in that video that I've linked in the chat, that first video where we look at circles that have the axes as tangents. So that's a really, really good one to look at maybe after this video. Okay, the circle S is in the first quadrant, so we can see that from the diagram. It touches both the x and the y-axis, and that line is a tangent to S as shown. So I suppose the important part here, there's lots of important parts, but it touches both the x and the y-axis. So there's my centre there. And let's think about how we would get to that centre. So we always start at the origin down here. We go across a certain amount on the x-axis, and then we go up a certain amount on the y-axis to get to that point. But we're not just going across any amount. If you look here, that amount that I've gone across here, that's actually equal to the radius of the circle. And also the amount that I've gone up here, that's also equal to the radius of the circle. So let's just call that centre. Let's give it the coordinates r and r, where r, let's make this clear to the examiner, r is my radius. Okay, so my centre of this circle, my centre is r. And the only way I know that is because it touches both of my axes. I go out a distance, I go up a distance, so my x coordinate is r, and my y coordinate is r there as well. So therefore my centre can be r and r. And what that does is it eliminates the need for introducing another variable, I suppose. Now we have the radius is r, but the centre is also r. So rather than having h and k, or minus g and minus f, we're dealing with just one variable here, which is always a little bit easier. We're also going to use the piece of information that they give us, that this line is a tangent to the circle. So what I'm going to do, always useful to draw the radius to the point of contact, because we know that that's always going to be perpendicular. So what we do know is that because it's definitely a tangent, the perpendicular distance from my centre, which is r, to that line, which they're calling t, that has to equal the radius, which we know is r. So the perpendicular distance, because the tangent is always perpendicular to the radius, from my centre to that line, that distance is obviously going to be the radius. It's clear to see that from my diagram. So we're going to use our perpendicular distance formula. Top of page 19 of your log tables. We've used it in the line as well. There's my perpendicular distance formula, and we're going to figure out what A is, what B is, what C is, what X1 and what Y1 is. So my A, B and C come from my line. My A is 3, my B is minus 4, and my C is 6, just like we use in the minus B formula. And my X1 and Y1 come from my point, so that's from the point, which is the centre. And we're just going to sub in, so we get the absolute value of 3 times r plus minus 4 times r plus c, which is plus 6, over the square root of a squared plus b squared. So that's going to be 3 squared plus minus 4 squared. Remember, that's coming from up here, my line. And we know that this time that distance is equal to the radius. So simplifying, on the top line, we're getting the absolute value of 3r minus 4r plus 6. On the bottom line, That's going to work out to be 5 equals my r. So simplifying in the absolute value, I get the absolute value of minus 1r. So that's coming from putting these two together. Plus 6 is equal to 5r. So I've just moved the 5 across and I've multiplied it by the r at the right hand side. So from our algebra, we know that when we have a situation like this with absolute value signs, we know that what's inside that absolute value, so that minus 1r plus 6, that could either be equal to 5r, or, so notice I've dropped my absolute value signs at this stage, it also could have been equal to minus 5r, because remember, when you put absolute values around something, it basically tells you to take the positive of whatever's in there. So if I had the absolute value of 5, that's definitely 5. But if I also had the absolute value of minus 5, that's also 5. Once we drop the absolute value signs, what's inside there, it could have been negative or it could have been positive, but the minute the absolute value signs go around it, we have to take the positive. So we have these two situations. What's inside that absolute value could have been 5r, but it also could have been minus 5r. And when I solve these equations, what I end up getting is, so with this one, I end up getting 6r is equal to 6, so r is equal to 1. And with this one here, I end up getting minus 4r is equal to 6, so r is equal to 6 divided by minus 4, or minus 3 over 2. Now, let's think about which one is which. Well, remind ourselves that r is our radius, and remind ourselves that it's also in the first quadrant. So whatever these two coordinates are here, they have to be positive, because we're going out the positive x-axis and we're going up the positive y-axis, so they have to be positive. So I have to go ahead with r is equal to 1. In other words, I'm rejecting this answer as r must be positive. So I'll give a reason for that. So I've just found my radius, but remember the question asked me to find the equation of the circle. Easiest equation to use here is from my page 19 of my log tables. Easiest equation is going to be this, because my HK is my center, so that's going to be RR, which is 1, and my radius is also going to be 1. So it's x minus 1 squared plus y minus 1 squared is equal to 1 squared, which is 1. And we knew we were only expecting one equation. It didn't say find the equations, it just said find the equation of S. Okay, so quite a bit to take in there, and there's loads more to the circle as well. But like I said, have a look at those 2 videos in the chat, and they should help you out with even more things to do with the circle. Always a huge topic on paper 2. Always at least one of the short questions. Okay, so I will leave it at that, and I will be looking forward to chatting to you the next time. Thank you.